Hey, what's up, guys? Today I'm going to show you how to do the electromagnetic simulations of periodic arrays of nanostructures or nanoparticles, um, mostly related to plasmonic nanoparticle arrays. So recently we published an article on the same topic, and I will just try to reproduce some of the results. We'll just take the very simple case of one monolayer of nanoparticles. So you can find this article by searching cool nanoparticles Kretschmann, because the effect of also the Kretschmann configuration was also shown here. Where can I find it? Okay, so this paper. So here, basically, it's a combined experimental and modeling study. So nanoparticle films were obtained and their modeling was done uh, to simulate the optical spectra and also near field and far field optical spectra. So to simulate this kind of infinite arrays, unit cell approach has to be taken. So we make like a rectangular or a hexagonal unit cell. So regardless of the unit cell, if the periodic boundary conditions are correct, then they should yield the same results. So that's what I tried to show here by comparing the results from both these two different unit cells, and I showed that the results are the same. And yeah, in the study also we synthesize this kind of nanoparticle films. It's like a monolayer of nanoparticles. So they are hexagonally close packed. So accordingly, the unit cell has to be constructed. So if it's a square array, then the unit cell will be different. And also the experimental and simulated spectra are compared. And so the study compares different interparticle distance in the film and also the near field properties, and also the effect of the Kretschmann configuration, because it's a quite different a way to excite the plasmons. In this case, the incident wave is coming from a denser medium, which is a prism in this case, and then the light is totally internally reflected at the bottom, and then it creates an evanescent field, and that evanescent standing wave uh, basically interacts with the nanoparticles. So in this figure, I think it is shown. So the incident beam comes and there's an evanescent field, and that is the evanescent field that is interacting with the nanoparticles. Unlike the case where the light is directly falling on the nanoparticles and exciting the plasmons, and we see um, the effect in the optical spectra. So yeah, the Kretschmann configuration or the ATR configuration is also studied in this case. All right, so we'll start with the simulations. So we'll be using COMSOL 5.5, but even if you use an earlier version of COMSOL, it should be completely fine. Um, so here we go. I also opened one of my old simulations just to not lose track of what I'm doing, just so that um, it's more efficient if I get stuck somewhere. All right, so in the model wizard, we choose uh, what kind of model is it. So it's a 3D model, and then electromagnetic waves frequency domain. So we add this, then go further with the study. And here we have to choose whether it's a frequency domain or also you can do an eigenfrequency study. Um, so I think in the earlier version, the wavelength domain was not added. Um, so if you are doing like a wavelength sweep, then it's quite useful. But actually, frequency domain and wavelength domain, they are basically the same thing. Just that in frequency domain, um, for your input wavelengths, it has to be converted to frequency by an expression that we'll give in the COMSOL. So that's basically the same, just one extra step that you have to take in frequency domain. Or the problem can also be defined in terms of inlet frequencies. So then you don't even have to do the conversion. So let's choose frequency domain. And we are done. All right. So the workflow is we will first make the geometry of the unit cell. Then we'll define the properties of the nanoparticles and everything. Also, we'll set the boundary conditions, some of the inlet conditions, and also define the physics. We'll do the meshing, and then we'll go towards the computation. So in the geometry, let's first make the nanospheres. Don't forget to make it nanometer. And then in the sphere, at 0, 0, 0 coordinate, we can give the radius of the nanoparticle. Now, we are working with 20 nanometer nanoparticles, so that is the diameter, so the radius will be 10 nanometer. But instead of giving the value here, what we can do, we can write a variable, a radius here, and then we define globally here what radius is. So radius is 10 nanometer. It's simple. So now this radius will take the 10 nanometer from there. And yeah. So just to add a note here, with plasmonic simulations, with plasmonic nanoparticles, we can do these kind of classical simulations up to 10 nanometer of diameter. So if the nanoparticles are smaller than 10 nanometer, then the quantum size effects become more and more stronger. It's not that you will not be able to do anything. So even if you have 5 nanometer nanoparticles, I mean their diameter, you can still do these kind of simulations. You will still get a spectra, but then you will not be able to capture the quantum side of it and the quantum effects. Still, it can be useful in some studies, but it's most accurate is always if the nanoparticles are larger than 10 nanometers. It's just important to note. All right, so the first sphere is here. So the other sphere, they should be in the 4 corners. So I will directly copy from one of my old case files because I don't want to do the entire the calculation and write it all down again. So X, you can note it. So we will add one more sphere, another sphere. The radius will be the same. So that is the X, then the Y, okay, so we see that it's red. The reason is COMSOL knows what radius is because we have defined it in the global definitions, but D is not defined. So if we define D, only then COMSOL will be able to recognize what D is. So D is basically the interparticle gap. So you will soon see what D is. Yeah. So here so D is basically this gap. So twice the radius plus D. So that is like the distance, and then To define their position, I had to take the cosine and sine. So the position of the other spheres will not be difficult here. So if I give a minus here, sorry, then I get a sphere over here. Then again duplicate. If I put a minus here, according to the coordinates, I will get a sphere here. And one more. This time x will be positive and y will be negative here. So that's it. We have the 5 spheres. And we have to make a rectangle. So a block we have to create here. Now the dimensions of the block we will again copy from the other case file. So it should be it should basically cover this sphere should be in the middle, and also 1/4 of all the spheres. So I already defined the expressions in terms of radius and d, so it's easy. And then 2 times radius plus d, so that is here, and 15 to radius, that is the height of this thing. Okay. So it's here, so I think we need to move it. So the center we have to choose here, the base. So now we have it. So on the top and the bottom, we also have to define the perfectly matched layer. So we have to select bottom and top and thickness of the layer. So 3 cross 3 into radius, that should be good enough. Okay, so we have it. Now we will do a union. Union of the block here and the nanoparticles. Why we do the union? You will understand it soon, because if we want to delete some parts of the geometry, then we first have to union it and make it one. Otherwise, all these entities, they are all different entities. So I will first hide the block so that I can choose. So they're all greens because they're selected, but this one was not. So I select that one, and now everything is united. So build all, build selected. So now I can delete the parts that I don't need. So you'll see it will be very easy. Delete entities here. So what we don't want is first, what we want to delete, we want to delete domains. Okay, so this part, this part, this part, and this part we don't need. Okay, so we have made the computational domain here, basically. So now the next step will be maybe define the materials. So for that, we need to basically load the materials from a material library that I created myself. So for that, we go to functions and interpolation and select a file. It's basically a .txt file, I don't know, where is it? It's a txt file of the wavelength and complex refractive index. So the real part of gold's refractive index is this one, import. So x-axis is the wavelength, and this is the real part of refractive index. Let's give it a name. Next one, interpolation. So now the imaginary part of gold's refractive index. Import KAU. All right, so the refractive indexes, they are basically provided as an input. So now these are interpolation functions. So for any wavelength, using this interpolation, it's a linear piecewise interpolation. So for any wavelength from this table, COMSOL will just itself will obtain the value of the FD, the real and imaginary part. So now based on this, let's define the material. So blank material. So to all the domain, whatever is there, let's first give it 1.33. That is the refractive index of water, but you can take any dielectric constant. And then let's overwrite the gold, because, oops, it's not right. Okay, so let's first hide the rest of the domain. So since we have already defined it here that everything is 1.33, now we have to override it. So here we'll first select what we want to overwrite. And these are gold. So we will use the interpolation function here. So basically for any lambda that you provide for the simulation, so for any lambda, this NAU, this interpolation function will provide the value of the real part, and here the imaginary part. So that is the idea here. And it's yellow because we don't know, COMSOL does not know actually what lambda is. So let's already mention what lambda. So here I'm giving a lambda so that COMSOL knows, and later on we also have to define somewhere, we have to provide that basically where COMSOL really asks for which lambda we want you to solve. So in the bottom we have to also define it. So lambda 300 is fine. So this lambda basically later we'll provide here because it's asking for the frequency, which frequency you want it to solve for. So here you see after I provided the lambda, it's not yellow anymore. All right. So other things to do. We also have to define some variables. First, let's define on the boundaries. We have to define the electric field components and the inlet. So I just wanted to hide it so that I have access to the boundaries. This boundary and this boundary. So why not here? It's because this part is basically the perfectly matched layer, and we are solving the problem here in this domain, and this is for perfect absorption of all the light, all the wave that is going out or going in, coming in. So yeah, we have to give the name E0x and 0y, and we can just write 1 and 0, but it's also easy to define in terms of the angles. If it's normal incidence, then it is only the azimuthal angle that matters here, that will define the polarization. Cos phi and sin phi I have defined here, cos phi and sin phi. And why it's yellow? It's because the COMSOL does not yet know what is phi. So two angles, incident angles, I have to provide. So for now, it's a normal incidence, and phi, we are also keeping it 0. So for 0 and 0, after introducing phi and theta, basically phi here, so it was yellow before, now it knows what phi is, so it's black now. Just to note here that COMSOL only takes radians, so if you have to provide some kind of a non-zero angle, you have to convert it to radian. Okay, and one more. So here we have to, yeah. So it's EWFD dot EX. So in the PML, these variables I'm just providing 0, because anyway in PML we are not solving for the model. So just to check, yeah, that is all right. One more thing that we have to define here: where is the perfectly matched layer? So now we have to define it. So these two are the perfectly matched layer. Don't have to do anything else. Okay, I think we are done with this part. Geometry is done. Materials we have defined. Then we move to the physics definition. I actually, before, I also tried by including the entire model here, and it did not work. So it has to do with the code, how it is written and stuff. So this has to be excluded. The perfectly matched layer has to be excluded. I think it makes sense because I think it's also solving only in that region. So not much to be done here. What we have to do here is we have to define the inlet electromagnetic wave, the incident wave. So we can use a port, and this is the inlet port, so the inlet is here from the top, and the type of the port is periodic because you will be using periodic boundary conditions. The wave excitation is on because we are exciting a wave on that boundary. and we have to provide input power. So now we don't know the input power yet. Let's do all the calculations here. So let's say we give some kind of intensity. So I0. So we'll provide some kind of intensity here. It's I0. And then we have to also calculate this length and this length. So the width and the depth of this block, so that we can find out what is the area of the surface. So the area multiplied by the intensity will give us the power. So with this expression, so this expression basically, so that is the width. So and depth, I think I will copy this part, so it's also here. And power, P will be just this. Power will be area into the intensity. So cool thing about COMSOL is that, yeah, you don't really have to define all the units over and over again. So here, the intensity we have already provided in the square bracket here, the units, and here also the radius and d we provided here. So all the calculations are done accordingly, and here they give you the final unit. So it makes things quite easy. So in the port, we define P, so that is the input power, and the inlet, the electric field components. So we have already defined earlier. So E0x, E0y. These angles also we have defined here in parameters, theta and phi. So if we provide here, which one is the elevation angle of incidence and the azimuth angle of incidence, COMSOL will directly take it from the global definitions. And yeah, everything is anyway water, so the refractive index is 1.33. Don't have to add any diffraction order here, because in this case the wavelength will be much larger than the nanoparticle, the periodicity. But yeah, if you have situations where the diffraction orders can be useful, then also COMSOL provides you a lot of options, so it makes things much easy. So port 2 will be the exit port. So that was the inlet and this is the outlet. And here again, the type of port is periodic because we are going to use periodic boundary conditions. I just want to check one more time. Yeah, there also I define periodic. So here the wave excitation is off, and the electric field amplitude we have to define here. That is simple. Importantly, if the wave is coming at an angle, then again you also have to define E0z and also do everything accordingly. So it's just for the most simple the simplest case. So that's why I'm skipping all those more complicated parts. So again, here it's 1.33. The next will be to impose the periodic boundary conditions. Um, so periodic boundary conditions we will impose on opposite walls. So first, maybe these two. So this wall and the opposite one. And then what kind of periodicity? It's Floquet periodicity, and then from periodic port, because in the port we have already defined that it is a periodic port, so it's quite simple. And again, periodic condition. Now on the remaining two walls, so Floquet periodicity here and periodic port. All right, so the physics is more or less defined here. So the next part is the mesh, and meshing is important here because that's where I was also stuck for some time. So the mesh has to be adaptive meshing here. So we have to copy the mesh on this wall to this wall because we are also using the Floquet periodicity on the opposite wall. So that's why the mesh has to be exactly the same. So we'll start meshing on the walls first, the side walls. So free triangular. Um, and after selecting the walls, have to also select the size. Let's do finer for now, just to check. Maybe extra fine. And maybe also customize the different parameters related to size. So these are basically the default values. The maximum element size, let's make it much smaller. Maybe 8 will be good enough. Yeah, it's much better. Minimum element size should be fine. Similarly, we will do the same for the other wall, which is free triangular again. Select the domains, the walls, and then the size. The size is extra fine. We'll do some custom setting again. So let's make it 8 again. Build all. Now we have to copy this mesh to the other side. For that we will use the copy. Where is it? Copy. So the source is this. And the destination is on the other side. All right. Okay, so one mesh is copied. Again, we have to do the same for the other two walls. For operations, copy. The source is this. And the destination is this. Okay. Now only the walls are meshed, so let's mesh the insides. So there we have to use 3D tetrahedral meshing. So we have to select the domains. So we are going to select this entire part and also the nanoparticles inside. So green means it has been selected. So total 5 plus 1, 6. There should be 6 domains. 1, 2, 3, 4, 5, 6. So seems all fine. Um, okay, so we should also define the size because that's why it's giving an warning. So maybe the mesh settings are too large. Okay, so if we select finer here now, the size, then things are fine. Okay, that looks quite all right. Now we have to mesh these two perfectly matched layer domains. We have to do sweeping. So first we'll select the domains. The source faces, yeah, to have access to those walls. Let's first have to hide. So yeah, sometimes I find it weird. Sometimes yeah. So now I cannot really do anything here. So I have to go here and hide it, and then I go back to where I was swept. Just yeah, sometimes it's a bit tricky. Um, and we select the source faces. This one, and this one, and the destination faces. So the destination faces are here. Okay. We also have to define how many distribution we want. So 5 is good enough. It's the default. Okay, so I think we are done with the meshing here. All right. So meshing has been done. That was also an important part of it. And here we have to define. So in the frequency domain, of course, COMSOL now wants to know for which frequencies we want to solve the model for. And so if we provide the frequencies here directly, that's okay. But now we have defined everything in terms of wavelength. So here there is no mention of frequency, right? So we want to provide a lambda, the wavelength, and we want COMSOL to solve for that lambda. So we will, that's why express the frequency in terms of lambda. So if we just write lambda here, I think this is a well-known expression that will basically give us the frequency. So I think we are done if I did not miss anything in the process. Seems like everything is okay. So now lambda is 300 because it's defined in the global definitions. So if I solve it now, then it will solve the model for 300, or maybe let's make it some other wavelength, maybe 500. So this is 500 here, and lambda is 500. And we did not define any unit there, then we can define it here. I need to check it one more time because it can be confusing sometimes. Yeah, of course, it's always it's if I because there is no unit defined for lambda there, so we have to make it. Okay, so now it will solve for 500 nanometer. So let's do a quick run and let's see if it's working fine. Okay, seems like it's working fine. We have some numerical artifact here, as you can see here, but I think those can be easily removed by doing a bit more finer meshing. Or another option is if we sometimes the domain length also matters. So maybe if we reduce the domain length a bit, then these artifacts will be gone. So instead of 50, we can make it 40. So yeah, it will be a bit shorter, but I think it will make things a bit better. We'll get rid of those artifacts. Yeah, so as you can see, so the domain size also matters. So little bit of hidden trial you have to do to optimize. So if these nanoparticles were bigger, then maybe the domain length has to be a bit bigger. After all, it's a numerical problem, so you have to optimize some things to really get the results that you are looking for. At least, I mean, accuracy wise. So now it solved only for lambda, but we want to solve for an entire spectrum. So that's why we have to use parametric sweep. So here we want to define what do we want to sweep for. So the lambda we want to sweep for. And for a range of maybe from 300 nanometer with a interval of 5 up to 800 nanometers. And this is the range. So if we solve now, then it will solve for the entire range. Yes, I think it's working. So it will take a while, maybe 1 or 2 hours, or maybe even more. So I will not wait till then. But a lot of more things can be done. For instance, if we want to introduce a substrate, then we can divide this domain here, and then we can make a substrate here. Or we can have a substrate here and also define incident angles, and also have to define the inlet electromagnetic wave vectors accordingly. So that way we can define for different situations. So that is it. I already showed you the work that we published on these kind of simulations. I think a lot more work can be done by varying this kind of structures, also other kind of nanoparticles and other shapes and sizes. Hope you find it useful. You can also check out another article of mine that I also worked on sensing with this kind of nanoparticle arrays. So that is it. Hope you found it useful. Bye bye.